All right, share screen. Like I said, I will post this once I get off of Zoom today, because I realized I graded stuff this morning and then didn't realize till about 20 minutes ago that I had not posted the answer key afterward. So yeah, some minor brain glitch. All right, so the first one involves the fact that you are given a pH. Now remember that all of this operates on the box system of, if you know one of 4 items, pH, POH, H plus concentration, or OH minus concentration, you can find the other 3 because they are all interrelated. So if I know pH is 4.1 and I take the antilog of negative 4.1, that will give me 7.9 times 10 to the negative 5th. Keep in mind that in the world of acids and bases, your numbers pretty much, in terms of the pH world, can't be higher than 1 molar and can't be smaller than 1 times 10 to the negative 14th. So those are kind of your end brackets. And then I used my Kw value, 1 times 10 to the negative 14th, and divided, and this gives me an H plus concentration of 1.27 times 10 to the negative 10th. And actually, I suddenly realized in looking at this that I probably actually should have labeled these a little bit better. Things that I sort of realize in the aftermath. Sometimes keeping up with all of this stuff just makes me a little bit crazy. Oh yeah, now my, okay. How about if I do it this way? We'll do OH. Supposed to be a capital H. Turn off my, all right, that looks a little bit more normal then. All right, so for the second one, we've got calculate the pH and POH. And this time around, you know what the hydrogen ion concentration is. 3.8 times 10 to the negative 10th. This one is a more straightforward application. Do negative log of, and that will give you a pH value of 9.4. I then took negative or 14 minus the 9.4, and that gives me POH of 4.6. So like I said, as long as you know one corner of the box that's involved there, you don't have to know all of it at one time. All right, scrolling downward a little bit. And for some reason, I have a line that goes all the way across here that wasn't actually supposed to be there, but when I was typing, it sort of was a glitch. I have a Ka value that I know, 1.7 times 10 to the negative 4th. I also have an initial concentration that I know of 0.2. I want to do a couple of different things here. I want to do concentrations of my unionized as well as my 2 ions, H plus and A minus. And I also want to figure out what my percent ionization is. So I went ahead and put my values in and did it in such a way that it looks like I have x squared on the top and 0.2 minus x on the bottom. Because when I first stabbed my way through this, I thought that it was going to come out in such a way that it would give me a higher than 5%. So I went ahead actually and crunched my way through it via the quadratic. And my positive root comes out to be 5.7 times 10 to the negative third, which is actually only 2.8%. If you use the unapproximated method, the problem with that is it then actually gives you a higher than 5%. So even though it looks like I might be able to use my approximation method, in fact, it gives you skewed data if you do that. So here where the black line is, that was, because that was sort of my glitch there, but my H plus and my formate ion both come out to be 0.0057. If I do that value over my initial concentration of 0.2, that's where I get my percent ionization, and then my initial minus my equilibrium bit gives me 0.1943. All right, strongs versus weaks. Remember that there are 4 acids which are always considered to be strong. Anything else generally is considered to be weak. So nitric and sulfuric are strong, but hydrofluoric, bisulfate, HSO4 minus, and carbonic are weak. I noticed somebody on homework wrote carbonic is strong. It's like, okay, carbonic acid is what makes your soda carbonated. So yeah, it's not a strong acid. It would dissolve your teeth yeah, if it was actually a strong acid. Calculating pH of 0.04 nitrous. This time my Ka was 4.5 times 10 to the negative fourth. That one's a pretty good bet that you can't approximate because there's only about 100-fold difference between your Ka value and your initial concentration. Not a big enough difference. So I wrote my Ka expression, which has the H plus and the NO2 on the top. I have the unionized version, HNO2 on the bottom. Set that equal to my Ka. All of these kind of look the same. It's just you plug your numbers in as needed. X squared on the top, 0.04 minus X on the bottom. I crunched my way through the quadratic. The only positive root I get is 4.02 times 10 to the negative third. And actually it didn't ask me for anything other than the pH. So I don't actually need to know what my NO2 minus concentration is. I don't need to know what my unionized version of the acid is. I can just take negative log of, and that will give me a pH value of 2.39. We end with some Lewis acid and base information there. To think about this in terms of the need for extra electrons being the driving factor for making it a base. So when you look at carbon dioxide, even though the oxygens have extra electrons, the carbon doesn't. So that has to fall in the acid category. Water, so H's don't have any extra high electrons, but the oxygen does. So in the world of Lewis acids and bases, water is supposed to be a base. Iodide, note it has a negative charge, and that's your tip off that it has an extra electron. That also makes it a base. SO2 is the iffy one, because when you draw SO2, you have to keep in mind the fact that it is capable of the expanded octet. So let me call up my whiteboard here. And so if we draw an SO2 molecule, okay, so we've got one of the oxygens has a double bond and one of them has a single bond. And we're going to put our octet together here. And then this oxygen has also an octet, but there's no double bond. And I have a spare pair, a lone pair, up there on top of my sulfur. Sulfur, however, one of the things we learned in first semester, sulfur is capable of having an expanded octet. You can force it to have 10 or 12 electrons, unlike an oxygen, which is too small. Therefore, it can either give up the 2 electrons that it has sitting on top of the sulfur, or you could force it into accepting an extra pair, which gives it then the acid capability.
I have a question.
Yes.
I believe in the book somewhere I read that water was neutral, that it couldn't be an acid nor a base.
From the Lewis point of view, or is that from the Bronsted-Lowry point of view?
Oh, see, I don't know.
Because remember, there's 3 versions. There's first semester version, which is called Arrhenius. There's the second version, which is most of the chapter, which is called the Bronsted-Lowry, which means you could call it both or neither. But Lewis, which is the very last section of the chapter, that's a little bit more weirdly specific.
Okay. Okay. I think I just kind of had it stuck in my brain then.
Yeah, Bronsted-Lowry, it can be neither or both. But for the Lewis one, the fact that it has the electron pairs sitting on top of the oxygen is what makes the difference there.
Okay.
All right, let me flip back over to the homework set. All right, so NH3, N has a lone pair, so it makes it a base. OH has that extra electron, which is your tip-off that it's a base. A naked hydrogen has nothing to give away, so that makes it an acid. But a boron in the middle of a BCl3 also has nothing to give away, so that makes that one an acid. So this was not a particularly extensive homework set. Mostly we kind of focused on pHs and POHs and some ionization ends of things. Other questions regarding the homework set? All right. I don't know if we'll get to the end of the chapter for this chapter or not tonight. I'm not sure. Let me find my file. Which would help if I actually opened the right file. And yeah, one of these days I'm going to get everything all organized into the correct set of folders so I don't have to dig around looking for my... What did I do with the file? All right. Back to trying to share this. All right, the last bit that we talked about was KSPs. So fun new letters of the alphabet to put as subscripts below your K values. And we really only looked at just 2 examples, and I think that's about as far as we got on that. We looked at silver chloride, which has a value, if you look it up, of around 1.6 times 10 to the negative 10th. And I have found out that it is apparent that not all textbooks / websites seem to provide the same values. And it doesn't even seem to be like a decimal error difference. Sometimes it's more than that. So yeah, I'm primarily using numbers that I looked up, but if you, for instance, looked up silver chloride, it is possible that you might see a couple of textbooks cite it as 1.7 or 1.8 times 10 to the negative 10th. It shouldn't be orders of magnitude difference, but they're not quite as close as I would like. And I know that this sometimes happens depending upon the source that you use if you're looking at different examples. We also looked at lead sulfide being another one that splits into 2 equal ions of a lead +2 and a sulfur -2, which has much less solubility. 3.4 times 10 to the negative 28th. And that's about as far as we got. Okay. Now we need to add another layer and look at some of the ones that have more than just a single cation and a single anion. So I picked on aluminum hydroxide. And aluminum hydroxide is often listed as having a solubility. This is not the KSP, this is just solubility of 5.9 times 10 to the negative 8th molar. I can use that value to calculate the KSP. You have to think about it in terms of how many pieces are you getting. So I'm going to flip back over to the whiteboard here. All right, so if we have an aluminum, and we're going to have 3 hydroxides. Okay, think about how this looks in terms of how it's constructed. You've got an aluminum there, okay, and then make one of your hydroxides kind of poke upward, make one of them poke sort of a bit to the right-hand side, and make one of them poke a little bit to the left-hand side here. Okay. One of the things this does is it reinforces the idea that if you drop this in water, I'm going to chop all 3 of these bonds that hold the hydroxides onto the aluminum. I'm going to chop them all apart. So this kind of reinforces that idea that I get 1 aluminum, but 3 OHs. So back to the more mathy end of it. So my aluminum concentration, think stoichiometry, okay, is 1:1. The exact molar amount of my known solubility matches the solubility of my aluminum. My hydroxide, however, because there are 3 of them, is 3 times that molar solubility. So 3 times 5.9 times 10 to the negative 8th will give me 1.77 times 10 to the negative 7th. And then if I put this in my formula where I have 1 aluminum and 3 hydroxides, then we have a situation where it kind of looks like you're duplicating things. And yes, you are. You have a essentially on the inside because it's 3 times the 5.9 times 10 to the 8th, but you also have to have a cubed. And this is again one of these things where I'm kind of realizing that things that I usually draw all over the board are actually not included in the files. So my KSP in terms of how it should look from a what the actual expression looks like point of view is like this. Oops, that's not supposed to be an equal, it's supposed to be a plus. So aluminum, which is 1, and remember 1s are always implied and not actually written. But my hydroxide is cubed. So then I went back and I put my values into this and crunch it all. And I came up with 3.27 times 10 to the negative 28th. And somebody, this is one of the reasons why I mentioned this, is somebody pointed out to me that that doesn't actually match this textbook. Okay, so be aware that sometimes if you are given data, by the time you crunch your way through a problem, it may or may not completely match KSP values that are just listed in a table. I have found that this is somewhat true of this textbook. I like OpenStax as a textbook system in general. However, it does have a few pitfalls in that some of the things that they have pulled their data from are a little bit harder to match up. All right, we saw initial concentrations a couple of times before. This time we are going to give them another letter of the alphabet. We're going to call this a Q, capital letter Q. Q, for some inexplicable reason, implying initial concentration. Why they're not using a capital I don't know, but this is the way pretty much all the textbooks agree. The ion product implies what did it look like when you first dumped it together. So it's a little bit Le Chatelier-like here, in that you have 3 scenarios that are possible. You can have a situation where your Q value is less than your KSP, at which point it is declared to be an unsaturated solution, meaning if you dumped a little more of your solid in and stirred it well, you could probably get a little bit more to dissolve. If your Q equals your KSP, you are exactly at the saturated situation. And if your Q is greater than your KSP, they are going to refer to this as supersaturated, which is a situation that is not particularly stable. You can make things be supersaturated for sometimes a very short period of time, but usually it doesn't last and things begin to precipitate. Think about it this way. Back to me harping on the sweet tea problem. Okay, if you have hot tea into which you are stirring a gargantuan amount of sugar, and you stir it well and the tea is still hot, as you put it in the fridge to cool down, for a while, some of that dissolved sugar that was extra will stay dissolved in the liquid, but only probably until you get down to kind of a lukewarm temperature, at which point, as it starts to be truly cooled temperature of the refrigerator, you're probably going to get some of the sugar coming back out of solution and making that crust on the bottom of your pitcher. All of these scenarios also, for some reason, again, use a different letter of the alphabet than we've been using to do all of our equilibrium problems. Technically speaking, it makes no difference. Okay, a variable is a variable, but you will see that most of the textbooks do tend to conform to the idea of, instead of using an X, let's use an S. I guess because the S is more in line with the concept of the term molar solubility. It's still molarity, okay? Number of moles per liter. We're just using an S instead. All right, how about going backwards? We plugged some values in, and then we calculated our KSP. What if you know your KSP, but you want to find your molar solubility? All right, let's take a look at one of the more straightforward ones first. If I look up silver bromide, cousin to silver chloride, it has a KSP of 5 times 10 to the negative 13th. Well, if I write my KSP expression, okay, here I've got 1 cation and 1 anion, which is kind of the same as saying I have an S and an S, gives me S squared. Therefore, I can take the square root of my KSP value, and that will tell me what my solubility is. 7.07 times 10 to the negative 7th. However, as we get more complicated molecules, if you look at this one, we have a situation where something is squared and something is to the first power. If I rearrange and crunch this, okay, this is another thing where Microsoft Word is not particularly cooperative in the way that I have this written out. Let me switch back over here to the whiteboard so that it makes, I mean, it's in your textbook, but all right, so if you're doing something that has a squared and a single, okay, you're going to have your giant square root bracket here, and we're going to have the KSP. I'm being really scribbly here. Okay, and then there's a 4. And this is not a square root, actually. This is a cube root. Now, depending upon what model of calculator you have, some of them have a cube root key. Some of them, you need a key that has this, y to the x, and you can use the inverse version of it to take other roots. Some models of calculators will have something that looks like a square root, and it'll have a little teeny x sitting right here on top of the root symbol. So that way you can take a 3rd root, a 4th root, a 5th root, which is kind of where we're going with this. All right, let me flip back over again to my stop share. Okay, I'm trying to flip back and forth and all right. Let's look at the next 2. We've got one here that has something cubed and something to the first power. My bottom one has something cubed and something squared. So ultimately, this ends up meaning that you need a fourth root and a fifth root in order to do these style of problems. So let me go back over to the whiteboard again to try to give you hopefully a little bit more clarity on what we're actually doing here. All right, so here's my big square root with a fourth root symbol there. And I'm going to put whatever the KSP was. And it goes over 27. Okay, why 27? Because 3 cubed is 27. That's why the 27 goes on the bottom. And then we had the final version, which has a fifth root. And it also still has the KSP for whatever thing you are looking at on the top here, but we are going to have 108 on the bottom, which then usually makes people go, where on earth did the 108 come from? All right, you had 3s cubed, which looks like this. And then you had 2s squared. Okay, so here we've got a 3 and a 2 as our exponents, so that's where our fifth root came from. But 3 times 3 times 3 is 27, times 2 times 2 gives you 108. Okay, take it on faith. It does actually work. All right, so those are, I refer to them as a shortcut method. Basically, if you have the formula, you don't have to worry so much about the fact that you're going someplace with it. Why is my little blue thingy? Okay. All right, so I have another example here for you. Calcium fluoride. 1 calcium, 2 fluorines. My KSP value is given as 4 times 10 to the negative 11th. First thing I did was write my KSP formula. Then I went back and did it in terms of S's. S to the 1 and 2s to the squared. That gets where my 4s cubed came from. Divide by 4, take a cube root, and my S value comes out to be 2.2 times 10 to the negative 4th. We're going to look at, and I will call it an imaginary compound because the answer you get is unrealistic. We're going to say that we have a compound that has 2 cations, so M2, and 3 anions. And we're going to hypothesize that it has a molar mass that's up there a little ways, 288 grams per mole. If I know that my solubility is 3.6 times 10 to the negative 13th, I can use this data to find my KSP. All right. There's my number of grams. That's in 1 liter. I'm going to divide by my molar mass, 288. And this gives me, for that point of view, not a very soluble, but not awful looking solubility. 1.25 times 10 to the negative 15th. But now we have to think about the fact that since this is splitting, I've got 2 cations and 3 anions. When I start putting them into this, there's my 2s squared and my 3s cubed. This is where I get my 108 and my S to the fifth. If I put this value in, 1.25 times 10 to the negative 15th to the fifth power, and then I multiply it by 108. This is why we're declaring this to be an imaginary compound, because one of the things I talked about briefly on last Thursday was things that have KSPs less than something to the negative 50th. So in this case, what you're seeing is an answer that implies you have it to the negative 73rd power. Yeah, mathematically you can calculate it. Realistically, it's probably not going to happen, because by the time you get to a number that minute, we're like trying to dissolve a spoonful of sugar in the Atlantic Ocean kind of thing. Maybe not qualitatively impossible, but not super likely, because we're implying that that's all the more soluble something actually is. So anything less than 10 to the negative 50th, be suspicious. It might be done as a mathematical exercise, which is actually what I did. But from a usability point of view, probably not. This is a chapter that involves a whole bunch of things that kind of interweave with each other. We started the chapter talking about buffers. One of the things about buffers is that they have a common ion. Acids and bases are not necessarily the only thing that has a common ion. Common ions affect solubility. So I have a scenario here where I have silver nitrate and silver chloride. And I'm trying to put both of them in the same beaker. Silver is my common ion. Well, we know silver nitrate is likely to be pretty soluble, because back to that rule from first semester, most nitrates are soluble. We also know, on the other hand, that silver chloride is not very soluble. If we hark back to that first semester rule that said all chlorides are soluble, or maybe it should say most chlorides are soluble, except silver, lead, and mercury, and then we get to this chapter that says that's not exactly the truth. It's not that it can't be soluble, it's more a matter of not very soluble. Think of it like placeholders, okay? If I have a beaker that already has silver nitrate in it, and I try to stir some silver chloride in it, even less will be able to be dissolved. Okay, I have watched way too many sports in this past year that have the pictures of people in the bleachers, okay, that are like cardboard cutouts. So think about it this way. If you are going to a March Madness game and you're one of the people who actually technically got to go for real, but there's all these cardboard cutouts that are in a whole bunch of the seats. Well, since the cardboard cutout is in that seat, you can't sit in that seat. And that's kind of how the silver ions are working here. The silvers that came from the silver nitrate are taking up slots where the silver chloride can't use them. How about a different example? Barium sulfate which is barely soluble. It has a KSP value. And sodium sulfate, which is really pretty highly soluble. So I know what the original concentration is of my sodium sulfate. It's given as 0.05 molar. My KSP is sort of middling, 1.5 times 10 to the negative ninth. I'm going to write out my KSP expression. So in this case, it's a 2-ion one. I have a barium and I have a sulfate. And I'm going to assume that essentially all available slots are occupied by the sulfates that came from the sodium sulfate. So take your 0.05 and put it in the slot where the sulfate was. So there's your sulfate, and here's where I'm putting in the 0.05. Divide to figure out your remaining item here. And this means that I have a barium concentration of 3 times 10 to the negative eighth. If I had done barium sulfate in just water, basically all I'm doing is taking the square root, it would have been quite a bit more soluble. It would have been almost 1,000 times more soluble. 3.9 times 10 to the negative fifth. We can also make use of this concept in terms of pHs, because pHs are ions. pH means we are dealing with hydrogen ions. pH also means we may be dealing with hydroxide ions. Calcium hydroxide is actually something we're going to see in a couple of weeks as the final lab of the semester that we do physically. Calcium hydroxide is a little bit soluble. Mostly it makes white sludgy stuff in the bottom of the beaker. What little of it does actually dissolve gives you 1 calcium and 2 hydroxides. If I had a beaker full of water that maybe I added ammonia or a little sodium hydroxide to, so that my beaker full of water was already more basic than I was expecting, I would have less solubility of my calcium hydroxide. On the other hand, if I want to improve my solubility, I can make my pH go in the opposite direction. All right. In some areas in Hampton Roads, depending upon if you have a well or not, you may end up with that weird, crusty white stuff around your shower head because there is calcium products in the water. Well, if it hasn't gotten too amazingly awful bad, one of the ways you can fix this is to unscrew your shower head and soak it in vinegar. Vinegar is a mild acid. The thing that makes the white crust is somewhat basic. So if you soaked it in a bucket of water, probably not much is going to happen because it's not very water soluble. But if you soak it in some vinegar, it may improve the flow of your shower head because it's dissolving some of that not very soluble stuff that's gunked up around the mouth of your shower head. So let's pick on some cadmium hydroxide. I have cadmium hydroxide with CD plus 2 and 2 OH minus. I look up my KSP. It's kind of middling, 10 to the negative 14th. I am going to have an S value for my cadmium, but I'm going to do something a little bit more, okay? I'm going to make it a little bit different here. I'm going to take the 2S, but I'm also going to assume that the water itself, because remember auto-ionization from a couple of chapters ago, might be a contributing factor. Okay, so you need to kind of think about this and figure out, does it actually make a difference? So here's my KSP expression. 1 cadmium ion, 2 hydroxide ions. I then go back and put my S's in. 1 S is by itself, the other is 2S, and maybe 10 to the negative 7th. But I kind of look at my values again. I'm comparing, okay, 10 to the negative 14th, 10 to the negative 7th. I probably have, or what it looks like, about a 7 exponent difference. And this is another one of those assumption ideas. I am going to assume that my solubility number is probably bigger than my auto-ionization. So I neglect it. I round it down. I've got the S and the 2S cubed. Yeah, the 2S cubed. The 2S squared, okay, gives me 4S cubed. Divide by 4, take a cube root. And yeah, it looks like I probably am pretty much in the right ballpark, because even if I added my 1.0 times 10 to the negative 7th back in, so there's 2 hydroxides, so I'm going to do 2 times S, 2 times 1.71 to the negative 5th, plus my auto-ionization. Look at my values here, okay? 3.42 to the negative 5th versus, if I add them together, 3.43 to the negative 5th. That's pretty negligible. We're talking second decimal place here. Oh, I did not mean to do that. I scrolled back up. When am I supposed to scroll down? All right, so POH, negative log of, gives me 4.46. My pH, subtract from 14, will give me 9.54. Kind of makes sense. I had something that makes OH minuses, even though it's not really soluble, it's sort of soluble. I should expect a basic, a higher than 7 pH. What if we go assumption-wise in the opposite direction? I'm going to go back and pick on aluminum hydroxide. Aluminum hydroxide's pretty insoluble. So we looked at it before. 1 aluminum, 3 hydroxides has a KSP of 1.8 times 10 to the negative 33. Again, I'm kind of heading in the direction of setting it up and then making assumptions. Here's your aluminum part of it. I'm going to give that a single S. My hydroxide, we're going to assume is 3S. And we're going to toss that auto-ionization in. Here's your KSP expression. Here's me putting numbers in. But now I'm going to make the backwards assumption. Instead of assuming that autoionization is nothing compared to my solid, I'm going to assume the opposite version. I'm going to assume that autoionization probably has more to do with this. So look at this one here. I put in 1 times 10 to the negative 7th, and I ignored my 3s. Cube that. That gives you an S value. I have an S of 1.8 times 10 to the negative 12th. I go back and put this all in. So 3 times S plus some ionization gives me this as my hydroxide concentration. It is so close to flat out 1 times 10 to the negative 7th that I can assume it has no impact on my pH or my pOH. So we had 2 different assumptions, and part of those assumptions are based upon what your KSP value is. Okay, when we looked at this one was down in the negative 30s. Chances are water itself has bigger impact. Whereas when I did the one above, I had 2 to the negative 14th. That's a much bigger KSP. Okay. So you have to think about where you're going in terms of your KSPs versus what kind of assumptions you might be able to make. A little bit more I want to get through tonight. We're definitely not going to get to the end of the chapter. This is a hefty chapter. However, I think I did go ahead and load all of the homework. So if you want to begin to look at homework this week, that's probably a good idea. Okay, more extensions of the same idea. We know the solubility rules. Now we have some exposure to KSPs. We can make predictions on whether or not a precipitate will form. When we did this in the first semester, we used the rules alone. We just kind of went, yes, it does, no, it doesn't, and there were no shades of gray, okay? Like, yeah, you get a precipitate, but you only get a little bit kind of thing. Now we sort of pull in the numerical predictions to this. So if I add barium nitrate to sodium carbonate, will I get a barium carbonate precipitate? Okay, and again, me realizing that there's probably should be an additional line in here of, all right, if you have BaNO3 2, we're going to add to that, oops, I need to get rid of my subscript there. We're going to add to that some Na2 CO3. All right. We get 2 sodium nitrates, and this is where the solubility rules come into play, is sodium nitrate is aqueous. It's never going to give you a solid unless you evaporate all the water. But barium carbonate is somewhat insoluble in terms of the rules. So that's why we are paying attention only to the barium and the carbonate and ignoring the sodium and the nitrate. All right, numbers. I have 10th molar and I have 20 mils, 0.020 liters. That means I have 2 times 10 to the negative third moles. My carbonate, also 10th molar, but I have a little bit more of it. I have 50 mils. So 5 times 10 to the negative third mils. But, okay, look at your values. I had 20 mils here and 50 mils here. I now have a bigger total volume. So the 2 to the negative third is now in 70 mils. And my carbonate of 5 times 10 to the negative third is now also in 70 mils. These are my new concentrations, 0.029 and 0.071. This is where my Q comes into play again. I have my expression. I have my new, I mixed it together, concentrations. That gives me this. If I look up my KSP, my Q is actually quite a bit bigger. Negative third versus negative ninth. This is the way you determine if something is going to precipitate yes or precipitate not because your Q was less than your KSP, or you could maybe say just barely going to precipitate, which would be exactly saturated. Q equals KSP. Okay. On Thursday, we will be getting into this thing known as selective precipitation. It's a not yes or no scenario. It is a very not yes or no scenario. It is a way of saying, well, if I add a little bit, I can get one item I'm looking for and not get the other one. Okay, here's a weird metaphor for this. Somebody gives you a bucket that has ping pong balls and Legos in it. Okay, and you're blindfolded. Okay, so can you reach into the bucket and pick out 2 ping pong balls? Well, yeah, okay, they're round. You can feel them and pull them out. This is kind of that idea from a chemistry point of view, from a solubility point of view. If I have 2 different things that are both, usually we're talking about positive things, 2 different metals that are in the same beaker, can I precipitate one without precipitating the other one? There is a way. Okay, I actually think it's kind of a cool and nifty idea, but we will get into that on Thursday. And then I think there's one more section left in this chapter that talks about KEQs, so more letters of the alphabet with below our K value. And this also harks back to coordination compounds again, which is one of the reasons why we dump them very briefly in at the beginning of the semester, because off and on as the semester progresses, we kind of see them in different uses. So that's kind of why we discuss them a little bit at the beginning. Questions about the homework that I went through or the stuff we have covered thus far in this chapter? Some of you I will see for lab tomorrow night. We are doing the experiment 18 potentiometric titration. My suggestion is make sure you bring a sheet of notebook paper with you, okay, or something to write on, because as you are doing this titration, you are going to be gathering data for probably about 75-ish data points. So you need something to record all this information on. I also loaded the report sheet to Canvas. I mean, you can take it home and do it, but if you actually bring it with you, it'll kind of help as I'm going through the explanations for that. But it is already loaded to Canvas. I did that it was either yesterday or the day before. And it is available for that part now. We are coming up on another test, okay? It's obviously not going to be this weekend because, for one thing, I just went over the homework. But no, actually, okay, I'm out of sync. We did equilibrium and kinetics. The next test is acid base and KSP. So actually, no, we have another week and a half ish before we get to heading toward test number 3. But it is coming in the not too distant future. So keep that in mind. Also, people who owe me labs, May the 3rd, okay? Day before, Force Day, May the 4th, be with you, is when your lab stuff really absolutely has to be turned in. So if you're behind, and some people are, try your best to catch up over the next week or two. People are making progress, but lots of people are still behind. Okay, so keep that in mind. I will see you, some of you, tomorrow.